well in here anymore. I don't know what happened.
We only have the one clock, don't we?
Yeah, there's also one on the screen as well, and that one does actually match.
Okay.
Up in the corner. Yeah,
Good.
exactly our thing.
So where's the camera going to be focused?
It essentially takes up the whole area from about
Oh,
here
okay.
over, so it sees both the screen and sort of the speaker at
Right.
the same time.
So all I have to avoid is running up into the audience then.
Yes.
So what sort of online audience do we?
So today, pleasure to welcome Dr. Roger Buick. Dr. Buick is a researcher and faculty here in the Department of Earth and Space Science, and he's also a member of the astrobiology faculty. And he studies early life on Earth and also trying to figure out what it potentially might look like should we find life elsewhere in the solar system. Dr. Buick.
So we all know from the movies that it's easy to recognize aliens if they're alive. They'll have characteristics that are something like life forms on Earth. They'll reproduce, they'll have metabolism, they'll respond to stimuli and so on. But we don't necessarily expect all life that might be out there in the universe to be alive. So one key question for astrobiology is, how will we recognize aliens if they're dead? And it's a particularly important question if we're worried about looking for Martians, because it looks like, from what we know about Mars, that it was probably only a habitable planet for a fairly short time early in its history, when there was liquid water on Mars and when conditions were warmer. So NASA, in all of its exploration of Mars, is looking for evidence of fossil aliens, dead aliens. But the critical question is, how will we recognize them if we find them? So the best way to try and guide us to how we would find fossil aliens is to look at relics of the earliest life on Earth. The reason being is that early Earth and early Mars were probably habitable about the same time, 3-4 billion years ago. And so by looking at relics of life from 3 and 4 billion years ago on Earth, we may have some comparative evidence for how fast evolution can go and what sort of life forms might evolve very early in the history of a planet. The other thing is that Earth is the only planet we know of that's inhabited, and it has a long and well-preserved biological history. We've got diverse lines of evidence that there was life on Earth early in its history. And if we presume that the processes that led to life and allowed life to evolve and radiate operated pretty much the same everywhere, then we can make an analogy from fossils of early Earth life to what we might find on early Mars or other currently dead planets. Now, there are difficulties with trying to work out the early Earth's biological record. Firstly, old rocks are rare. To find a rock 3.5 billion years ago is not an everyday occurrence. You won't find one within 3,000 miles of here, for instance. And then again, old rocks have usually had a pretty traumatic history. The chances of them being cooked or squashed, metamorphosed and deformed are high, and those processes destroy relics of early life. Really old rocks that might contain evidence of early life usually only occur in fairly inaccessible parts of the world, like the edge of the Greenland ice cap, or the desert in outback Australia, or in game parks in South Africa, where you have to go and look at them with an armed guard with an AK-47 alongside you to keep off the marauding rhinoceroses and things like that. Only sedimentary rocks are likely to contain much evidence of early life. So you're restricted in the sorts of rocks you can look at. And then the last problem is that early life on Earth may not be really comparable to what we have on the planet now. So it might be as unrecognizable as early aliens on Mars. We think not, because we think we have a pretty good continuous microbial record of life on Earth, but it's at least plausible that anything alive on Earth now might be so far evolved from what primitive organisms were like that it's relatively unrecognizable. So where do we find really old rocks that might contain fossils of similar age to when Mars was inhabitable? Well, you can see here a map of the world with Archean rocks marked on in green if they're between 2.5 and 3 billion years. GA is just an abbreviation for billion years. But the time interval we really want to know about is this earlier Archean interval before 3 billion years ago, when we're pretty sure that Mars had liquid water on it. And you'll see there's only a few spots on the Earth where there are these really old rocks. The oldest rock on the planet is in Arctic Canada, this Acasta gneiss up here, older than 4 billion years, but it's been so cooked and squashed it wouldn't have any records of life in it. The oldest solid material on the early Earth are zircon crystals that go back to almost the age of the Earth. The Earth is 4.567 billion. These are zircons going back to 4.4 billion. But again, they're just mineral crystals. They won't contain fossils. So what sorts of evidence can we go looking for in ancient rocks for early life? We can go looking for the dead bodies of the organisms. We presume that all of the earliest life was microscopic because even in the middle age of Earth, in the Proterozoic, all life was microscopic. We can go looking for the traces of their activities, trace fossils like stromatolites, which are mounds of sediment built up by bacteria trapping and binding the sediment. We can go looking for atomic fossils. We can look for fractionations of the stable isotopes of biologically essential elements that are imparted by metabolism. I mean, compared with carbon dioxide around you, you, sir, are fractionated by 20 parts per million, 20 parts per thousand in favour of the light stable isotope of carbon compared with the carbon dioxide around you. So if we were to find you dead, we could analyse your tissues, look at the atomic fossils and say, probably alive. And that applies to other elements as well. You can go looking for molecular fossils of organisms, biomarker molecules, derivatives of biological molecules. Again, we could kill you and fossilise you, and we could work out what your cholesterol level was, because fortunately cholesterol preserves pretty well in the geological record. So let's say we didn't kill you, but you died of natural causes right there, we could determine whether it was a stroke brought on by high cholesterol levels that killed you. And this is 2 billion years later. We could do that. We could go looking for biominerals. Now, we have biominerals in us, bones, apatite, calcium phosphate, but some microbes do too. Even though they don't have skeletons, there are some microbes that mineralise magnetite, for instance, to use the magnetite crystals as little compasses to find their way around. Or we could go looking for bioalteration. So instead of the biological production of minerals, it's the biological destruction of minerals. So let's just look at a few quick examples of all of these things. Microfossils, firstly. They're the cell walls or the extracellular sheaths of microbial organisms. The intracellular stuff doesn't preserve well, but their external walls are made up of a polymer that's more resistant. To preserve them, you've got to bury them really rapidly, and you have to entomb them in very fine-grained mineral crystals. Otherwise, other bugs eat them or they oxidise away. It's really nice to have the dead bodies of a once living microbes. But unfortunately for microorganisms, having the dead body often doesn't tell you much about what it was, because microbes are very small and very simple in structure, so just having a 1 micron carbon ball in a rock doesn't necessarily tell you what sort of organism it was. Also, dead bodies, they tend to be little balls or little tubes. And there are a number of non-biological processes that can make similar structures out of carbon. So you usually have to find some evidence of some sort of behaviour before you can be sure that something you think is a microfossil is in fact a dead organism. And then lastly, there's the problem of contamination. There are microbes everywhere, now and in the past. And so it's quite common to get younger microbes creeping down microfractures into older rocks and posing as old fossils. So where you get younger microbes contaminating older rocks is a significant issue. Here's an example of some microfossils. These are all between 1 and 2 billion years old, but they're directly comparable with modern types of bacteria that photosynthesize, cyanobacteria. In fact, they show distinctive cell division patterns or multicellular organisation that you can relate to modern genera of cyanobacteria. So we can presume from the close identity that they lived in the same way. They lived by oxygenic photosynthesis. The second sort of evidence, trace fossils of the activities of once living organisms. Stromatolites, these are layered sediment mounds accreted by growing or moving or metabolizing microbes. They show a predominance of convex upwards flexures, which is an anti-gravity organisation. It's microbes accreting sediment in the opposite way to how gravity accretes sediment. So they're fairly distinctively biological. They're not formed by single microbes, but by carpets of microbes living along the seafloor and growing more thickly over little topographic highs, little mounds, because they're photosynthetic and because light is attenuated with depth in water, they grow more thickly where the water's slightly less deep. So they trap more sediment where the water's less deep, so they grow upwards in a mound-shaped fashion. Modern ones tend to form where animals are scarce because animals will eat photosynthetic microbes. But before the advent of animals, these sorts of structures were commonly preserved in sedimentary rocks. The difficulty with them is that there are many non-biological mimics of stromatolites, things like stalagmites or some sorts of folds in rocks. Here's some examples. The most famous modern ones are from Shark Bay in Australia. Can you see those all right up the back? Is that better? Okay, good. And you can see the process whereby they form. You get a carpet of microbes along the sea floor growing thicker where there's a little mound on the sea floor, and as a result, where they're thicker, just like the carpet by your front door, they trap more sediment in the carpet where it's thicker. Here's another example. Instead of being discrete mounds, these ones are growing together. And here's just an example of a microbial mat accreting sediment. Then we mentioned atomic fossils. These are fractionations of the stable isotopes of biologically essential elements like carbon or sulfur or nitrogen. And metabolic processes usually favour the light isotope over the heavy isotope. So living organisms or their byproducts are usually enriched in the light isotope of these elements. So carbon has two stable isotopes, carbon-12, carbon-13. You're all enriched in carbon-12. With nitrogen, it's a bit paradoxical. Biological nitrogen tends to be enriched in the heavy isotope, and if we were to, sorry to keep picking on you, but if we were to slaughter you again, we could look at your nitrogen isotopes and determine whether you were a vegetarian, an omnivore, a carnivore, a top carnivore, or a top super predator. Because each step you go up the food chain, your nitrogen isotopes get enriched by about 3 per 1,000 in favour of the heavy isotope. So what are you? Top predator or?
Oh, definitely.
Right. Get those burgers. It's slaughter them. Now the interesting thing is that the biological fractionation of these isotopes is much larger at low temperatures and pressures than abiotic fractionations of these isotopes. So in rocks that have never been heated or cooked, heated too much, or squashed too much, a large isotopic fractionation indicates that it was imparted by life. And they survive reasonably well through low-grade metamorphic processes. The difficulty with looking for atomic fossils is that to prove that it's a biological fractionation, you have to have both the reactant and the product to analyse. So you know the isotopic ratio going in and the isotopic ratio coming out of the metabolic process. And often you don't have that preserved in sedimentary rocks. So here's just an example. This is how you work out the isotopic ratio of carbon in organic matter, for instance. And here's just a diagram showing 0 per 1,000 fractionation to minus 40 per 1,000 fractionation. Minus 40 means enriched in the light isotope. And you can see that atmospheric carbon dioxide is about minus 7. But when it gets metabolized by all these different sorts of microbes and plants, it's fractionated during photosynthesis, and they all produce organic matter that's enriched in the light isotope. Molecular fossils. These are hydrocarbon molecules that are derived from the photosynthetic pigments of organisms or from membrane rigidifying molecules. So, cholesterol. You all have it. You have good and bad cholesterol. The good cholesterol stops your cell membranes from falling to bits when you jump. Right? Cell membranes are little fat globules. And if you've ever been doing the washing up and you have fat globules in the washing up and you stir it up, they all reorganize and change. Your cell membranes are like that too. So every time your hand doesn't just turn to some amorphous goop because you have membrane rigidifying molecules like good cholesterol. And they preserve in geological environments in oil and in kerogen, the non-crystalline insoluble organic matter that gets preserved in sedimentary rocks. The geological molecules are different from the biological ones in that they contain no functional groups like alcohols or carbonyl groups or anything like that. And they don't have multiple bonds, but the carbon skeleton of these molecules remains the same. These survive up to temperatures of around about 200 degrees centigrade. The difficulty is that they're easily contaminated with any ancient or modern hydrocarbon-bearing fluid. So the black gunk that comes out of diesel trucks, for instance, is loaded with biomarker molecules. So if one of them goes past your lab window while you're doing an analysis, you get contamination. So here's some examples of biomarker molecules. Here's cholesterol. Each one of these is a carbon at the corner with hydrogen stuck to it. You can see that cholesterol has a double bond down there and a hydroxyl group there. The geological derivative, cholestane, has lost the double bond and it's lost the hydroxyl group, but you can see that the carbon skeleton is identical. So you know that that's derived from that. Different groups of organisms have different characteristic biomarker molecules. Bacteria, for instance, have hopanols, which degrade geologically to hopanes. So if you find one of these in a rock, you know you're dealing with something derived from a bacterium. Cholesterol is diagnostic of our sorts of organisms, the eukaryotes. And there's a third domain of life, the archaea. They have membrane stiffening molecules that look like that. Here's the geological derivative up there. Biominerals, we mentioned briefly that some microbes mineralize magnetite, produce chains of magnetite crystals within their cells that have a distinctive morphology. Some other microbes mineralize other minerals. We're not going to talk about these any further because they haven't been found in really ancient rocks, but it's worth noting that the only possible evidence for past life on Mars that we have is these sorts of magnetite crystals in a Martian meteorite. It still cannot be disproved that the magnetite microcrystals in the Martian meteorite ALH 84001 aren't biological. It's the only possible evidence we have for past life on Mars. And then lastly, the opposite of biomineralization, the biological destruction of minerals. Microbes can alter and erode little pits and tubules in basaltic glass, leaving a characteristic texture of these little feathery sorts of drill holes in glass. It's hard to prove often that these things are biological, but sometimes they have carbon preserved in them, and sometimes they show evidence of behaviour in that these little tubules will be oriented towards particular mineral grains that the microbes might have been mining. So, those are the 6 lines of evidence we can go looking for. Now let's go through and talk about what's the oldest evidence of life on Earth, what's the oldest visible evidence of life on Earth, what's the oldest bodily evidence of life on Earth, and how can we use atomic and molecular fossils to tell us something about how that lived. So the oldest evidence of life on Earth, the 2 areas we're going to talk about are Western Greenland on the edge of the ice there, and northwestern Australia here. This is the oldest purported evidence of life on Earth. Supposedly graphite crystals, crystals of pure carbon inside apatite grains, crystals of calcium phosphate that were allegedly found within a metamorphosed sedimentary rock, and these graphite crystals contain a carbon isotope ratio that's about the same magnitude as that produced by modern photosynthetic organisms. You'll see it was published in a very prestigious scientific journal, got a cover photo, but on the cover they put a question mark at the end. Wisely so, because it turns out when you date these apatite crystals that contain the graphite, it yields an age much younger than the age of the host rock. So these graphite crystals could have got there as young as that, which is the age of these apatite crystals. So if it's evidence of life, it's not necessarily evidence of life at 3.85 billion years ago. It might only be evidence of life at 1.8 billion years ago. So if we go a little bit younger, 3.7 billion years, this is still more than 3/4 of the way back to the origin of the Earth. You get graphite again with a similar isotopic composition, but these are in less metamorphosed rocks that clearly started out as being sedimentary rocks that are shales. The difficulty with this, however, is that there is no... Remember how when we were talking about atomic fossils, you needed to have both the reactant and the product to be sure of what the magnitude of the isotopic fractionation was. In this instance, there is no sedimentary carbonate that would represent the isotopic composition of carbon dioxide going into photosynthesis to compare with what comes out of photosynthesis. So this could be evidence of life, but it's not conclusive. This is the guy who found it, the only Inuit professor of geology on Earth, I think, standing next to his greatest discovery. So, if we go a little bit younger, in northwestern Australia we find carbonate rocks that are clearly sedimentary, they're layered, they're deposited in the ocean, and they contain relatively unmetamorphosed organic matter within the carbonate. So we can look at the isotopic composition of the carbonate, the isotopic composition of the organic matter, and they're fractionated by about 20 parts per 1,000 in favour of the light isotope in the organic matter. Exactly the same as you get in modern marine environments where you get microbial photosynthetic organic matter in sedimentary carbonates. So this is typical of what happens on the modern Earth. So this is probably the oldest robust evidence we have for life on Earth. Still in the first billion years of Earth history. So what's the oldest visible evidence of life on Earth? We're going again to northwestern Australia, to rocks slightly younger than those that contain the carbon isotope evidence for life. This is only about 50 million years younger, so 3.47 billion. And there we see stromatolites at a place called North Pole in Australia. It's the hottest place in Australia. Gets up to, regularly up to 120 degrees every day in summer. So with the typical wonderful Australian quirky sense of humour, they called it North Pole. It's not very funny, really. And in layers of sedimentary rock, you find these sorts of dome-shaped flexures in the sedimentary layers that propagate up through the rock. Here's one that starts in the pretty flat there, starts there and gets progressively more steeply domed as you go up. If you look at a cut surface of it, you'll see that the layers are thicker over the crests of the domes than they are in the troughs. In between the domes, you get little flaked up bits that have desiccated from the top that contain layers of organic matter in them. And this is what they look like looking down on them. They look exactly the same as modern stromatolites that grow together. So this is the oldest visible evidence of life on Earth. I found this when I was a PhD student, so that's why I've got the job I have today and I'm talking to you today. So that's my best discovery. What about the oldest dead bodies? We have to go to slightly younger rocks to try and find that. The oldest microfossils are very controversial. There's been a lot of argument about what the oldest ones are. So we'll look at 4 possible examples. Some from northwestern Australia that you'll see in every textbook and encyclopedia as being the oldest microfossils from 3.45 billion. And then we'll go through some others and I'll show you what I reckon are the oldest real dead bodies. These are the oldest ones that you see in the textbooks. Just under 3.5 billion years old. They're meant to, alleged to be carbonaceous structures that show chains of microbial cells. This is about 10 microns from there to there, 10,000ths of a millimetre. So, you know, these are minuscule, and it's said that these things are chains of cells, just like some of those cyanobacteria that I showed you earlier. What's significant about them, however, is that they're in rocks that have been heated to roughly 450 degrees centigrade for millions of years. So about 600 degrees Fahrenheit for millions of years. What happens when you put a chicken in the oven at 600 degrees Fahrenheit and leave it there for 1 million years? What colour does it go? You've never cooked a chicken? None of you have had to work in KFC? Black. Any organic matter when you cook it goes black with heat. You can try it by putting your hand in a flame and holding it there for a few million years. You'll notice that these things, though they're composed of organic matter, aren't black. They go from a sort of orangey brown through a yellowy brown through a mid-brown to a greyish brown. They're not black. These things are almost certainly contamination. And if they are biological, they're an example of microbes that got into their host rocks after their host rocks had already been heated up to 400 degrees centigrade for millions of years. So these, whatever they are, and they're really not terribly convincing as microfossils. They don't look very much like modern microbes. Whatever they are, they're contamination. So if you go a little bit younger, also in northwestern Australia, there are these things, these filaments. That scale bar there is, I think it's 50 microns. These look like little clusters of filamentous bacteria. The problem is that they're not composed of carbon. They're not composed of organic matter. They're composed of pyrite. And we know that the pyrite precipitated in a subsurface hydrothermal environment, like a black smoker that you get out on mid-ocean ridges. And this is an unlikely place for there to be living organisms at any time, because it's really hot, it's really reducing, and the waters are really caustic. So, because they're not composed of carbon, it makes you wonder whether they truly are microbes. However, they do seem to show some evidence of behaviour. Depending on the type of layering of the rock that they're in, they seem to have different orientations. If they're in banded layers, they seem to be roughly parallel with the layering. If they're in these coliform structures, where they have a more irregular layering to the rock, they can be either parallel or perpendicular. So maybe these things are alive, but perhaps not conclusive. Similarly old from South Africa, people have argued that some of these things, come on, work, you bastard. There. Some of these things are little carbon spheres that were fossilized in the process of division. Well, maybe it's there's no real complex behaviour to these sorts of things, so are these really dividing, or are they just two little non-biological spheres of carbon that are about the same size that just happen to get juxtaposed? Maybe evidence of life. You really have to go to quite a lot younger, to about halfway through Earth's history, before you get absolutely for sure and certain dead bodies of microbes. These are from South Africa, 2.6 billion years old, and these are cells made of carbon that are hollow, that have clearly been fossilized in the process of division, and they are found in the layers of a stromatolite. So you have evidence of complex interaction with the surrounding environment, that these things were trapping and binding sediment, that they were dividing, that they have the right composition, the right size, and they're very well preserved, and they have the right colour. So these things aren't contamination. So if you want to be picky about it, 2.6 is the oldest for sure and certain evidence of dead bodies. So, before we finish, let's just talk about what we can use atomic and molecular fossils for to work out how some of these things lived. We're going to look at isotopic evidence of metabolism from two different sets of rocks in northwestern Australia. Immediately below those stromatolites, immediately underneath them, directly underlying them, you get rocks like this, which are made up of crystals of a mineral barite, which is barium sulfate, and within the barite crystals you get microcrystals of pyrite, iron sulfide. So you get sulfides within sulfates. And you can look at the sulfur isotopes of those two minerals and see whether there's any record in them of microbes breathing sulfate, SO4. So, I hate to pick on you again, but you're actively, you are awake. You're actively metabolizing now. And you're metabolizing by, yes you are, by aerobic respiration. You're taking organic matter, your hamburger, and reacting it with oxygen, and that releases energy, and you're breathing out carbon dioxide and water, aren't you? Thank you. That's aerobic respiration. But there are many microbes that are capable of anaerobic respiration. Instead of breathing oxygen to burn hamburgers, organic matter, they can breathe sulfate or nitrate or other oxygen-containing anions. So there's at least, and the byproduct, instead of being water, in the case of anaerobic respiration using sulfate, the byproduct is not H2O, but it's H2S, rotten egg gas, hydrogen sulfide. And if there's any iron in the environment, it will react with it to form pyrite. So we can compare the isotopic ratios of pyrite with sulfate to see whether there were bugs anaerobically respiring the sulfate. And if you look at the sulfur isotope record through time, you get big fractionations of sulfur in rocks younger than 2.5 billion years that indicate that this metabolism was occurring. If we look at these rocks here, you get, again, a big fractionation like you see after 2.5 billion years in the pyrite. So this shows that there were indeed microbes metabolizing the sulfate and turning it to sulfide, reducing it to sulfide by respiration. As far back as the age of those stromatolites. So we have visible evidence for life, and we have some evidence of what that life, how that life was living. It was living by anaerobic respiration. If we go a little younger and look at carbon isotopes this time, there's a metabolism that imparts a particularly obvious fractionation on carbon isotopes. It's called methanogenesis. It's something that's exclusively done by one particular branch of microbial life, the archaea, things that look like bacteria but are actually more closely related to us rather than bacteria. And methanogenesis imparts a really, really big fractionation in favour of the light isotope of carbon. Something greater than 40 parts per thousand enriched in the light isotope of carbon. And if we look at the isotopic composition of organic carbon through time, we notice there's this one outlier at about 2.8 billion years ago. Well, there's a couple actually in here, all lighter than minus 40. This shows that methanogenic archaea, bugs that make their living by taking dead organic matter and converting it into carbon dioxide and methane, were alive at 2.8, 2.7 billion years ago. So this shows us not only that we have a particular metabolism operating, but that we've got one particular group of microbial organisms, the archaea, performing it. You can also look at isotopes of nitrogen in really old rocks. Here's a drill core. This is just a graphic log of the rocks in the drill core, and there's lots of black laminated shale in it. And if you look in that, you'll see that the nitrogen isotope compositions are low here and get steadily higher and then drop back to low values. This can be explained by the operation of two microbial metabolisms. One is nitrification, taking ammonium and oxidizing it to nitrate, and then the nitrate gets reduced back to nitrogen gas by a process called denitrification. Both of these metabolisms are performed by both bacteria and archaea, but nitrification, as far as we know, is only performed by one group of bacteria and one group of archaea. So we're now starting to get evidence of not just whole broad domains of microbial life living, but particular small groups of microbial life living back as far as 2.5 billion. And then lastly, we can go looking for molecular fossils of life. And here we're going to look at 2.7 billion year old rocks. What you can do with these 2.7 billion year old rocks is you can extract the molecular fossils, the hydrocarbon biomarkers out of those rocks. This is my graduate student who did most of the work. And you can get molecules out of it that are diagnostic of, again, other particular groups of microbes. You can get hopanes, which are diagnostic of bacteria. You can get particular hopane molecules. These are these greater than C31 2-alpha methyl hopanes, model there. These are diagnostic of cyanobacteria. Or, no. They're characteristic of cyanobacteria, though not exclusively diagnostic of cyanobacteria. So these tell you that you're dealing with a particular phylum of bacteria that metabolized in a particular way. Cyanobacteria perform oxygenic photosynthesis. And then you also get lots of sterol molecules, including cholesterol, the derivative of cholesterol, out of these things. They tell you that you're dealing with eukaryotes. So by 2.6, 2.7 billion years ago, we had all three major domains of life, the eukaryotes, the archaea, the bacteria. We had particular phyla of bacteria, including the cyanobacteria that were responsible for putting and are responsible for putting all the oxygen in the atmosphere. And we had direct ancestors of eukaryotes. I mean, the fact that there's cholesterol in these rocks is proof that your ultimate ancestors were around on Earth 2.7 billion years ago. So, if we look at the universal tree of life, the family history of everything, determined by genetic sequences. Here we have our three domains of life. We have the eukaryotes here, which includes and fungi and plants and slime molds and anything with complex cells, all related to each other. Then here's the bacteria over here, and here's the archaea. These other bacteria-like things, but you can see are more closely related to you than they are to bacteria. This is the last common ancestor of all life here. And we can start to use these fossils to put some dates on this tree. We can say that from the sulfur isotopes, we're at least there by 2.7 billion years ago. We've got the molecular fossil evidence for cyanobacteria at 3.47 there. Cyanobacteria by 2.7 billion. Methanogens by 2.76. Look, all these things over this side. Methano. All those things are methanogens. And at least somewhere on this branch of the tree, ultimately leading to you by 2.7 billion years ago. So, what does this tell us? Most microbial evolution occurred early in Earth's history. Most of the microbial branches on this tree had to have been there within the first 2 billion years of Earth history. And a lot of it, a fair amount, within the first billion years of Earth history. The equivalent time to when there was liquid water in relative abundance on Mars. So this implies that from the early Earth evidence, it's at least plausible that there were aliens on Mars in the first billion years of its history when there was liquid water on Mars. You can get from no life at all on a dead planet to one that's got thriving microbial life in a billion years. the Earth record shows that. Secondly, that if you look at Mars and the Moon, the old planetary surfaces on those planets are heavily cratered. There were huge meteorite impacts as late as 3.8 billion years on the Moon and Mars. Big enough impacts to have vaporized any ocean that might have been on Mars. Earth would have suffered the same process. But soon after the end of this meteorite bombardment that cratered the surface of Mars and the Moon, and presumably Earth, we had organisms that were as complex as modern microbial organisms, widespread and abundant on the planet. So even if you can evolve life in the first billion years of a planet's history, you can potentially exterminate life by meteorite impact and re-evolve it again very quickly. So life on Earth arose and diversified rapidly. Planets that have early but short-lived windows of habitability could once have been lively, even if they're not now. And then to go back to our movie Aliens, that we all see are usually of either greater or moderately less intelligence than us, never the same for some reason. Intelligence clearly doesn't follow rapidly from the first appearance of complex cells. We had complex cells that were capable of multicellular organisation almost 3 billion years ago. But it took 3 billion years for someone as intelligent as you, sir, to evolve. So just because there are gazillions of planets out there, don't assume that there's life as intelligent as you on most of them. If there's life out there, almost certainly, most of it's going to be microbial. For 8/9 of this planet's history, all life was microbial, and it's probably the case out there. So don't believe the movies unless they show you aliens that look like bacteria. Any questions?
Thank you very much.
Questions?